Hey guys, these are our notes about, well, the first set of notes about complex numbers. I'm honestly not sure how much of this stuff we're going to get through. Probably most of it, but we'll see. I'll see how long it takes. So this first slide is just what we're going to be talking about. What is I? What are complex numbers? There's this like little weird pattern with powers of I. We'll talk about simplifying expressions, and this for sure is going to be the next. This will definitely be in the next lesson. We'll probably get to most of the other stuff though. There's not too much going on. So we know this. Square root of 36 is 6 because 36 is 6 times 6. Square root of 121 is 11. I know in my class in block 8, I talked about how square root of 121 is not plus or minus 11. It's just 11 because this symbol, that square root, that radical symbol means like the principal square root, which means a positive one. And I distinguish between the question, the square root of 121 equals what number? This is one question. Another question is, if x squared equals 121, what does x equal? This is a different question. The answer to this question is 11, because the square root here means the principal square root. The answer to this question is plus or minus 11, because there are two numbers you can square to get 121. So these are slightly different questions. I'm not that excited about that, but that's why I write 11, not plus or minus 11. Square root of negative 36 is like the question we're trying to answer here. So, because like, I don't know, 6 doesn't work. 6 times 6 is positive 36. Negative 6 times negative 6 is also positive 36. So what do I multiply by itself to get negative 36? This is the kind of the all-important question that was eventually answered with these things called complex numbers, or sometimes referred to as imaginary numbers, where we created, by we, I mean some a lot smarter than me, created a number called I. And they said that, they basically, the first thing they said was that I squared is negative 1. Which means, like, kind of by definition, I is the square root of negative 1. So I squared is like I times I, right? It's like I times I. That equals negative 1. I cubed, though, is I times I times I. So I know that this right here, I times I, is negative 1. Negative 1 times anything is just negative that thing, so this equals negative I. All right, these two i's here make a negative 1, and then times I gives you negative I. Now I can multiply, what if I did 4 i's? That's what this is saying. So it's like I times I times I times I. Well, I know that 2 i's make negative 1, and these 2 i's also make negative 1. So it's negative 1 times negative 1, which is 1. Basically, you just multiply whatever you get here by I every time. So it's like to get down to here, times I, and then I'm going to multiply this number by I to get up to I to the 5th. And since this is a 1, 1 times I is just I again. So I'm kind of back where I started with I. Multiply this by I get I times I is I squared. That's negative 1, right? Multiply this by I. Well, negative 1 times anything is just negative that thing, so it's going to be negative I. Right, this is like the same things I'm getting before. Multiply this one by I, and I get negative I squared, which is negative 1, which is positive 1. Here's what I want you to see. This is like I to the 1st right here. And this is I to the 5th. And they both equal I. This is I to the 1st, so it's I. This is I to the 5th, it equals I. I squared is negative 1, and I to the 6th is also negative 1. I cubed is negative I, and I to the 7th is also negative I. I to the 4th is 1, I to the 8th is also 1. And there's like a pattern here, where every 4 numbers, the pattern repeats. It basically goes like this. It goes I, and then negative 1, and then negative I, then 1, and then it repeats. Where this is like you keep multiplying by I each time. This goes circles on forever and ever and ever. We do this all day, right? So one of the like tricks in this unit is like given a big power of I, can you tell me what it equals? And it's got to be one of these 4 things because we just see this as a circle. So it's either going to be I, like these are the only possible answers. These 4 questions here, which are big powers of I, there's only 4 possible answers. I, -1, -I, or +1. You got to tell me which one it is. And usually the way people do it is they think about when the power is a multiple of 4, it equals 1. Then you just kind of go up or down from there, maybe. But like knowing that the pattern is like I, -1, -I, 1. And these are all the multiples of 4 right here, this bottom. So the closest multiple of 4 that's less than 23 is 20. And to get to 23 from 20, I got to go up 3. So it means, what that means is like I to the 20th is going to equal 1 because it's a multiple of 4. Let's go back here, remember. I to the 4th is 1, I to the 8th is 1, I to the 12th will be 1. Every power of I where the power is a multiple of 4 is going to equal 1. And you just count up. If this is 20, and it's like 21, 22, 23. The answer is -I. It's 3 more than a multiple of 4, so you go 1, 2, 3. So let's see if we can do this again for this other, this is a bigger one, 145. What did we say? I, -1, -I, 1. Let's keep using that little, keep using this guy for a minute. So remember that the bottom is the multiple of 4. This is multiple of 4. And when I say that, I mean the power of I is multiple of 4. So 144 is a multiple of 4. This is 145. 144 plus 1. So 144 is the 1, 145 is the I. But there's a 1 step here, 145. All right, 144 was right here, 145 is up there. We're done. So 48 is a multiple of 4. 48 divided by 4 is 12. So multiple of 4 is right here, that equals 1. And now 62, I think 60 is a multiple of 4. So 60 is right here. And you count up to 1, 2, -1. So the powers of I trick is about recognizing multiples of 4. There's a couple other ways to think about it. If someone cares about that, I can talk to you all about it in class. So that's what I is, square root of -1. This is the powers of I. I'll do these 2 things, then we'll just talk about standard form pretty much in the next video. Pretty much your whole math career up to now, you've been stuck on this branch of the family tree, so to speak. We've been over here the whole time, the real numbers, which are just numbers. And there's rational and irrational numbers, and there's positive and negatives, and there's integers, and there's fractions, and all kinds of things, but it's always just numbers, real numbers. But really, all numbers in the world are what we call complex numbers. They're written as A plus BI. Okay, where A and B are any 2 real numbers, and I is this imaginary number, quote unquote, imaginary number that we just talked about. So I don't necessarily like this notation, imaginary. I feel like complex numbers immediately split into these 2, pure imaginary and not pure imaginary. Pure imaginary means that there's no real part. So an example of a real number is like, a rational real number is like 1/2 or 752 over 11 or something. Irrational numbers are ones that you can't write as fractions, so like pi and e and the square root of 3, and there's a literal infinity of all these. They look like this. A pure imaginary number would be just like 3i or 5i or 10i. And these are like, there's no, this is like, you could write 3i as 0 plus 3i. And so thinking about, it's like a is 0 and b is 3. When you think about the complex number is a plus bi, well then 3i is 0 plus 3i. It's like a plus bi. You can write the a. If it's not there, you just assume it's 0. The same thing is true with a number like 1/2. This is like 1/2 plus 0i. Okay, so like the a is 1/2 and the b is 0. And we'll see later on maybe why the a's and the b's are important for us to know when it comes to graphing these things. We'll get to that later. And then what they call complex imaginary number on this table that I just call like a complex number would be like 3 plus 4i or something. This would be like a is 3, b is 4. And just to say it again, the a and the b I'm talking about are the a and the b from up here. Where we say complex numbers are always written in the form a plus bi, where a and b are any two real numbers, and I is the imaginary unit. Probably want to say that. So what this is. Who cares about these things? So of course mathematicians do, because that's awesome. Physicists use them a lot. Fractal geometers, we talk about this in class. Electrical engineers is pretty important, and of course you guys fall into this category, people who are awesome. Yeah, I'll stop this here and we'll talk about the kind of the mathematical manipulation of these things in the next one.